Good morning, and welcome to Best Practices and Techniques for NX Patterning. My name is Jonathan Buck. I work for ATA Engineering. This is the latest in our series of monthly webinars. Before I begin, I'd like to give you a brief background on ATA Engineering for those of you who aren't familiar with us. We have a long background and an extensive history. Originally, we were part of a company called the Structural Dynamics Research Corporation, which pioneered many of the FEA and CAE tools that are endemic in the marketplace today. We spun off from them in 2000, and we have continued to have a very friendly relationship with the group that is now Siemens PLM Software, which of course is the developer of the NX CAD platform, which will be the subject of today's webinar. In the time since we spun off from SDRC, we've continued to offer a wide variety of engineering services for design, analysis, test, and process improvement from a wide range of industries, everything from aerospace and defense to entertainment. Here's a brief outline for our webinar today. I'll start off by giving you some motivation for why we want to take a close look at some particular aspects of creating patterns in NX. Then I'll take a little bit of a deeper dive into the specific commands you can use to create patterns in NX, and I'll give you a flavor for some of the trade-offs among these different ways that you can use to create patterns. Then I'll describe in detail some techniques for dynamically changing pattern spacing, position, and size. And then we'll get even a little bit more complex still by looking at techniques for successful pattern creation on surfaces with complex topology or complex curvature, where some of the more straightforward pattern operations don't necessarily give you the right type of pattern in one go. And then finally, we'll look at advanced methods for efficient creation of large-scale patterns. And here when I say large-scale, I'm talking on the order of 5, 10, 15,000 or more pattern instances. And then I'll finish with some concluding remarks. As I promised, I'll give you some motivation for why patterns are an interesting subject. In almost every industry, you see regular repeating elements, everything from industrial sieves and screens, microfluidic nozzles, spacecraft isogrid structures. I mean, you name an industry, there's some aspect of their product where they have these regular repeating structures. And NX's pattern operations provide tremendous power and flexibility to the designer or the engineer for easily generating such patterns. Rarely does anyone create each and every single one of these features individually by hand anymore. They leverage some of these pattern features that are available to you in NX and also many of the other CAD tools as well. However, within NX, there are several distinct pattern commands that appear on, at first glance to do much the same thing, but as I'll show throughout the course of this webinar, you can get different results with these different commands, and depending on the exact nature of your pattern, you might prefer to use one command over another. And so that takes us to the last bullet point here. The right understanding of these commands, their settings, even though they may appear similar, can really help you as the designer to create patterns as efficiently as possible. And I hope along the way, throughout the course of this webinar, you'll also realize that creating patterns can be even more flexible than you realized. Now, I'll first start by outlining the various pattern commands in NX. The four main ones are shown on this slide. From left to right, you've got pattern feature, then pattern face, then pattern geometry, and then pattern curve. Now, at this point, I don't want to dive into the nitty-gritty of each and every aspect of these dialog boxes, but you notice at first glance just how similar they are. In fact, many of the same design elements in one dialog box also appear on the other. And to the novice designer, this can actually create a fair bit of confusion because it's not entirely clear which command you should use if all you want to do is create a simple pattern. What I will tell you at this point in the presentation is, from a very high level, these are the distinguishing characteristics of one command versus another. When we look at pattern feature, that's the most robust, most sophisticated way to create patterns in NX. It creates copies of entire features, can be used to alter size and shape. Consequently, because of how robust and full-featured it is, it does offer the slowest performance. Pattern geometry copies objects, for example, curves, edges, faces, bodies, so on and so forth, with intermediate performance. Pattern face copies only faces and Boolean operations that may have been performed on source faces and offers excellent performance because of its more limited capabilities. And finally, pattern curve copies curves only, as the name suggests. What I'd like to show you at this point is just the efficiency or performance differences you can see in using these four different pattern commands. What this graph shows you is the generation time to create a 1,000 instance pattern, and this is on a log scale, so you notice the difference between 10 and 100 appears on the same scale as 1 and 10. And what we see is pattern feature is the slowest. That's just as I said on the previous slide, because pattern feature does offer the most robust, sophisticated capabilities for changing many aspects of a pattern instance. It does require more overhead, and it is the slowest. In the intermediate performance range, you see pattern curve and pattern geometry. And then with the fastest performance, you see pattern face in a class of its own. So at this point, what I would offer to you is, for most circumstances, pattern face is actually often the right choice. And by choosing pattern face over pattern feature, you can realize substantial performance benefits. The first recommendation I often give to people who are struggling with patterning challenges is to first start with pattern face, see if that in fact offers the capabilities they're looking for, and if it does, terrific, they can move forward with knowing that they have a very efficient tool at their disposal. If it turns out it does not offer the capabilities that they're looking for, then they might explore some of these other methods, for instance, pattern feature, knowing that in doing so, they're incurring more computational overhead in the pattern generation process, but that it's a necessary step to get whatever sophisticated pattern generation techniques that they need. Now I'll take a little bit of a deep dive into some specific techniques you can use to change pattern spacing and position. And there's four particular techniques here that I'll focus on. The first one is the list method. The second one is the increment method. The third one is the spreadsheet method. And the fourth one is the clocking method, which may also be referred to as the delta or motion-based method. And I'll go through each one of these four one by one. The first method is the list method. And I'll say that over the course of the next few slides, you'll see the pattern face dialog box here off to the left. But as we saw a few slides ago, many of these dialog boxes appear similar. And if you look in pattern feature or pattern geometry, you'll see these same sorts of capabilities. So even though this dialog box says pattern face, this is not necessarily exclusive to the pattern face command in particular. So what we see here is we take a shape, say this circle in the top left corner of this rectangular sheet, and we want to make a rectangular grid of circular shapes based on this initial circle. And in this case, what we want to demonstrate is that as the pattern propagates to the right, we can change the spacing between these pattern instances. So to start with, we could give it a distance of 1, and then make the distance increase to 2, and then to 3, and then back to 1. And this is enabled through this spacing list method in the dialog box. And so what you see is you can enter any number of spacing values, and then the space cycles iteratively between the list that you've provided, and if NX sees that you've gotten to the end of the list, then it returns back to the beginning of the cycle, which in this case brings us back to the spacing of 1.0. Second method is the increment method. To enable this, look in the pattern dialog box for the pattern increment section and click the pattern increment button, which will bring up a second dialog box. Now at first glance, this appears similar to the dialog box we saw in the previous slide for the list method. We're entering increments, and we can add them to this tabular section of the dialog box here. But the key difference between the increment method and the list method is that the increment we supply here gets added successively to each and every instance in an arithmetic progression. So again, if we start off where our first base feature is the circle at the top left of the shape, and we increment the pattern as it propagates across the right, the first spacing is 1, then it increases to 1.5, then to 2, then to 2.5, and so on and so forth. And if I had added even more instances to this pattern, it would increase to 3, 3.5, so on and so forth. And that's all controlled by this value we prescribed in the increment box here. The third method is the spreadsheet method. To enable this, we look in the dialog box just below pattern increment, and we look for this little Excel icon, and we click Use Spreadsheet. And we can, by clicking this button, we can bring up this native Excel window, which offers complete and full control over the position of each and every instance. And so what you see in this Excel window that pops up is a tabular listing of the offset distance for each and every instance in the pattern. So by going in here, picking an arbitrary row and column, I can change the number, return back to Excel, and it moves an individual pattern instance according to the number that I have entered in Excel. Now the last method for spacing changes is the clocking method. To enable this, we look for the instance points section of the pattern dialog box, click the crosshair button, and then we look in our graphics window where we will see these kind of bronze gold dots in the at the center of each pattern. And then we want to right click on any one of these points and click the clock button on the context sensitive pop-up menu. By doing that, we'll get a dialog box that appears that enables us to clock or change the position of that one individual instance in a way that's very similar to the spreadsheet method, except we bypass the need to access and work with the instance spacing in an Excel format. And so by changing these numbers, direction 1 or direction 2, we can change the offset of that individual pattern instance. Now the other thing you can do here that's extremely powerful is you can change the type in this drop-down menu from within pattern definition to user defined. And then by doing that, you can avail yourself of these motion capabilities that you may be familiar with in other contexts within NXCAD. In particular, you can use dynamic to bring up an XYZ Cartesian coordinate system to dynamically drag and rotate any given pattern instance along any arbitrary axis or direction. Now I'll describe some techniques for changing the pattern size and shape. The two methods I'll describe here are the increment method and the spreadsheet method. The increment method for pattern shape appears very similar to the increment method for changing pattern size. What we'll do here is look in the pattern dialog box, again, for this pattern increment button, and we'll get this dialog box that pops up called pattern increment. And then what we look for are these parameters underneath the extrude operation. And if I look for this parallel dimension, which I've given a named expression slot width here, I can change the value of this increment. And then as I look at this pattern on the right-hand side of the slide here, I see that what starts off as a circle slowly grows and morphs into a slot as I work my way to the right. And what's happening here is I've parameterized the underlying sketch of this original shape to be a circle with a slot width that starts at a value of 0, and then as this pattern propagates to the right, that slot width increments by 1/10 of an inch. And so eventually the circle becomes more and more slot-like. Now the key point here is in order to enable this, we have to use pattern feature because this is one of those advanced, sophisticated aspects of pattern feature that I described earlier that causes pattern feature to have a little bit more overhead than the other pattern operations. And the other caveat here is that when you perform this workflow, the sketch of an extrude operation must be internal to that extrude operation. And it's important to do that because that is what provides access to these parameters of the extrude operation itself. If the sketch is not internal to the extrude, when you click the pattern increment button, all you'll see are these parameters that control pattern offsets and not these aspects of the sketch geometry itself. Now, while we're talking about creating holes, there's a quick tip I'll give you here about using the simple hole command for very flexible creation of hole patterns. What we saw in the previous slide required creating a sketch, then an extrude operation and making sure that sketch is internal to the extrude, and then going through the pattern operation to morph that shape from a circle to a slot. And that does have performance consequences because you take a little bit of you take on a little bit of additional overhead when you make the sketch internal to the extrude, and you take on a little bit extra overhead when you use that pattern feature command. However, if you know ahead of time that all you want is a pattern of circles, in fact, it's far better to use this simple hole command rather than the extrude command to create a circle. And that's illustrated by this plot over here on the right. If I create a 1000 instance pattern of circular holes, and I make a sketch followed by an extrude and then a pattern, I get a runtime of about 125 seconds on my machine. If I make the sketch internal to that extrude, the runtime almost doubles. And as I said just a few minutes ago, making the sketch internal is an essential step in changing the shape of that pattern. And again, as that example showed, that pattern morphed from circular to slot-like. However, if I use the simple hole command, I can get an even better performance than this external sketch mode of operation. It is limited to circles, that's the caveat here, but if you know ahead of time that all you're interested in are circles, then I would encourage you to use the simple hole command for the best efficiency possible. Now, there's another caveat here that we should talk about when we're on the subject of efficiency and performance of pattern operations. When you open the pattern feature dialog box, you'll see way down at the bottom there's a pattern method, and there's a drop-down menu that lets you select either variational or simple. Now, it turns out for most cases, the simple method actually provides all of the desired pattern functionality that you might want and operates significantly faster than the variational method. In fact, if you refer back to that example of changing the circle to a slot, you can actually perform that operation with the simple pattern method. But I mention this point here because the variational method is often the default on most systems, and you can see from this plot here, again, for an example where we're creating a 1000 instance pattern, you can see just how much faster the simple method is as opposed to the variational method. Now, at this point, I'll address some techniques for effective use of patterns on complex surfaces. So the examples I'll show you on the next few slides relate to this example surface I made here, which is a surface I made up, but you can imagine you might have a surface like this in certain industrial contexts. Maybe it's a screen, maybe it's a sieve, or maybe there's certain industrial design applications where you need a surface with the right kind of complex topology. And you can see if you look at the surface, it has some interesting wrinkling to it. It sort of bends in and then bends out. And the other interesting aspect of the surface is none of these edges are mutually parallel or perpendicular. So what we'll see in the next few slides are some techniques you can use to maintain the right desired shape when you create patterns on these kinds of surfaces and avoid self-intersections of the pattern instances and those sorts of things. Now, to provide some motivation here, I'll show you what it looks like when you create some patterns with the default settings on these surfaces. If we use pattern feature with an extrude operation where the initial base feature is this circle at the top left of the surface, as it propagates across the surface to the right-hand side, you see the circle becomes more and more elliptical, and you also see that the pattern lines become skewed relative to the right edge. If I use a pattern feature with that simple hole command that I described a few slides ago, it looks a little bit better. The circles stay circular across the surface, but now we get yet another undesired result. The circles start to overlap with one another and in fact even intersect when you get to these last two columns here. Now what we're going to do to resolve these shortcomings is to work with this layout drop-down menu in the pattern feature dialog box. There's three options here: rigid, offset, and translate. And those three options are shown on the slide here. If we use rigid and translate, we get almost the desired behavior, except in this very last instance, the shape drifts off of this isoparametric curve that I've drawn to show the kind of line that we want this pattern to propagate along. If we use this offset method, and we use isoparametric curves to provide a path for the pattern, then we see that each of these shapes has a center that lies exactly on this line, and the spacing between the shapes is constant, and the shape remains circular as we move across the surface. And that, in this case, is the desired output that we want. Now, when you use this layout along method, you can use two directions of pattern propagation as you can with some of the other layouts. But when you use the layout along method, using two directions may start to give you undesired results. And that's what these pictures here on the right show. If we propagate along path 1, which is along these isoparametric curves that run from left to right, we get the desired result on this first row, but then when we move to the second, third, fourth, fifth row, so on and so forth, then we start to see these pattern lines drift, self-intersect, and exhibit some of those undesired qualities. So the workflow here is to perform not just one large pattern operation across the entire surface, but to create a series of 1D patterns along each of these isoparametric curves. Now that does have some consequences in terms of the manual effort required to create a unique pattern for each of these isoparametric curves, but what we've seen is that is the required workflow to get these pattern shapes to exhibit the desired qualities. Now you've seen me refer to these isoparametric curves before as an aid to creating these types of patterns on complex, curved, topologically complex surfaces. And here's a brief slide describing the utility of these isoparametric curves. The other thing you can do with these isoparametric curves is you can create a point set, which lets you create an arbitrary number of points equidistantly spaced on a curve. And by using these point sets, you can very easily and efficiently create seed locations for the creation of a base instance for a pattern. Now, another aspect of patterning on complex surfaces we'll talk about has to do with controlling the pattern orientation. There's another aspect of the dialog box under the orientation category that lets us check to follow the face of the surface, and we can also choose the projection direction, whether it's along the pattern plane normal, along the face normal, or along a vector. Now what we see in this first picture is that for arbitrarily curved surfaces, when we use the first option, along pattern plane normal, we typically see undesirable results. If you look off to the right here, you see that these circles become ellipses and they start to intersect. If we choose the second option, along face normal, we see that the circular shape is maintained, which is good, but now the pattern lines begin to drift into one another. Now the takeaway here is, again, to use the workflow we outlined on the previous slide to create those isoparametric curves and use those as guides when using the layout along selection. Now, having gone through some of the finer points of comparing and contrasting the various NX pattern commands, ways you can change the shape, ways you can change the spacing, as well as some advanced techniques for controlling the position of patterns on complex curved surfaces. Now I'll go one step further and build upon that technique, that workflow we just outlined for creating a series of 1D pattern operations along those isoparametric curves. As I said before, that does represent some amount of manual overhead to manually create each of those 1D pattern operations that propagates along a single direction. So what we did here at ATA was we developed our own custom tool that can be plugged into NX using the NX Open API that automates the process of creating that series of 1D pattern operations. And so what we see here on this plot is a comparison of the generation time to create a pattern where the count is shown on the horizontal axis and the generation time is shown on the vertical axis, and the native NX command is shown in the green line, and the blue and the red curves correspond to the generation times for the tool that we developed here at ATA. And there's two curves here because the tool that we developed has two modes of operation. The first mode is what we call the interactive mode, where you're operating on the surface within NX in real time. And the second mode we refer to as batch operation. And this operation performs the pattern by allowing you to specify the pattern parameters in advance and then calling NX in a quote-unquote batch mode where you run it behind the scenes without having to draw the graphics of each and every pattern instance. And we found that by bypassing the graphics window in this manner, we can realize even more performance gains. And this is a brief demonstration of the kinds of patterns that we've been able to create using the techniques that we illustrated in this presentation and encapsulated in our custom patterning tool using NX Open. This is that same arbitrarily curved surface that we saw earlier, and we're creating a pattern with 10,000 shapes, and the shapes transition from circles at the top to slots at the bottom. And we see a generation time of about 10 hours here, which sounds like a long time, but as we saw on that plot on the previous slide, to create a pattern of 10,000 shapes using the native NX operation would take at least double this amount of time, if not more, plus there would be that additional element of manual overhead to create those series of 1D pattern operations. Now I'll finish here by giving you some conclusions and takeaways that you can bring back with you as you create patterns in your own job. The first takeaway is that I would urge you to carefully consider the needs of your use case in deciding whether to use pattern feature, pattern face, pattern curve, or pattern geometry. We saw these four native commands early on in the presentation, and we saw that they had very different performance metrics. They were very different in terms of their efficiency, but by and large, they're very similar in their capabilities. Pattern feature is the most sophisticated, robust of the bunch, but for most everyday pattern scenarios, you can get away with any of these four, and in fact, pattern face has the best performance, and so that is where I would encourage you to start. Similarly, when you open the pattern dialog box, look down at the bottom and change that method from variational to simple. For most everyday pattern scenarios, the simple method will provide all the capabilities you need to do things such as change shape, change position, so on and so forth. And you'll realize significant performance gains by sticking with that simple method as opposed to the variational method. It's only if you're running into some very specific particular patterning challenges that might warrant the variational method that I think you would want to switch back from simple to variational. For creating patterns on complex curved surfaces, we saw that the follow face and the long layout techniques can help to ensure successful pattern generation. And finally, we saw that using NX Open is a very powerful way to automate large operations, not only large pattern operations, but anything that you might want to do in the NX platform. And when you do use NX Open, or try to use NX Open to do these kinds of automation efforts, I would encourage you to consider using history-free and batch mode to realize even greater efficiency gains. All right, that concludes our webinar on best practices and techniques for NX pattern generation. I hope you've gotten some good notes. I hope you've gotten some good takeaways. At this point, I'd like to open it up to questions. Sounds like we don't have any today, so again, thank you for your time. We really appreciate you taking a half hour out of your day to tune into our monthly webinar series. We hope to see you next time. Thank you. Bye-bye.